Okay, let's unpack this. Today, we are embarking on a deep dive into, well, a challenge that sits right at the heart of the connected world you're navigating, IoT interoperability.
Mm-hmm.
You've shared a stack of fascinating source material on this topic,
Oh,
and it immediately makes clear just how critical this is for anyone involved with the Internet of Things, really.
absolutely. I mean, just think about the sheer number of devices flooding into homes, factories,
Right.
cities.
And their ability to actually work together to seamlessly share information and coordinate actions across different systems. Well, it isn't just a nice to have anymore.
No, it's foundational, totally foundational.
So our mission in this deep dive, and we're guided entirely by the sources you've provided here, is to kind of cut through the complexity.
Yeah, get to the core of it.
We want to understand the real impact this challenge has on, say, application development, device integration, and, ultimately what the end user actually experiences.
Yeah.
We'll explore the current state of affairs, look at some of the best practices highlighted in the material, and maybe peer into the future a little bit, see where things might be heading.
That's good.
The goal is really to arm you with the insights needed to navigate what is, let's face it, a pretty fragmented ecosystem. This conversation is built on your material, and we're here to help you understand what matters most within it.
And what's fascinating here, right from the start, the material you brought us makes it clear this isn't just some, isolated technical problem.
No, definitely not.
This challenge of making things work together, it has real ripple effects. It impacts the developers, the ones who actually have to build these systems,
Uh-huh.
the businesses investing, heavily in IoT solutions,
Right. Big investments.
and critically, the people who interact with these devices every single day. I mean, if a smart device doesn't talk to another smart device, or if your data gets stuck in one system,
Then the whole promise kind of falls apart, doesn't it?
it really does. The whole promise of the Internet of Things just falls short. It's a fundamental barrier, really, to unlocking all that potential.
Absolutely. And to really understand that barrier, I think we have to start with the basics. Like, what exactly do we mean by IoT interoperability?
Right. Good starting point. So the source material kicks off by defining this essential concept.
Okay.
At its core, IoT interoperability is about the ability of devices, applications, and networks to connect, communicate, and exchange data
Mm-hmm.
in a way that's understandable and actionable. And crucially, across different platforms, manufacturers, protocols, all that stuff.
So it's about making sure, say, a device built by company A can effectively share info or get commands from a system built by company B.
Exactly. Without needing, cumbersome manual fixes or custom one-off integrations for every single little connection. That's the ideal, anyway.
Right, the ideal. And it's not just about, like, plugging things in together, is it? The material emphasizes different layers where this needs to happen.
Precisely. And breaking it down into these distinct layers, like your source does, is really crucial. Because, a failure at any one point can basically break the whole interconnected system.
Okay, so what are these layers?
Well, the first one is device-to-device interoperability. This is about two physical IoT devices communicating directly with each other.
Like one sensor talking straight to an actuator.
Yeah, exactly. Can a sensor device send data directly to an actuator, or can one controller tell another device to do something without having to go through, say, a central server or the cloud for every little thing?
Okay. Often using things like Bluetooth or Zigbee, maybe.
That's right. Those kinds of local communication protocols often handle this layer.
Okay, so that's device to device. What's next?
Moving up, you've got application-to-application interoperability. This is more about the software side. Can different software applications maybe running on your phone or cloud platforms or edge gateways, can they exchange data and trigger actions in each other's systems?
Give me an example.
Sure. Think about an app monitoring energy usage from smart meters. It needs to be able to share that data, perhaps with an application controlling your smart thermostat, your HVAC system.
Right, so they can coordinate.
Exactly. Or maybe an analytics platform needs to pull in data from a bunch of different device management applications, that kind of interaction.
And that usually relies on APIs, data
Yeah.
formats.
Yes, typically APIs and agreed upon data formats are key at this application layer.
Okay. And there's one more layer.
Yeah, the third one is network interoperability. This deals with how devices can actually connect and exchange data across different types of communication networks.
Because not everything is on Wi-Fi.
Not by a long shot. IoT devices might use cellular, 4G, 5G, NB-IoT, or those low-power wide area networks, LPWANs. like LoRaWAN.
Right, for long-range, low power.
Exactly. Or short-range stuff like Zigbee or Thread. So the question here is, can data reliably flow and still be understood as it moves across these different network types? Because they all have different characteristics, right? Bandwidth, latency, power use.
I see. So understanding these layers, device, application, network, it's vital because the specific problem and maybe the solution could be different depending on where the friction is.
Precisely. Is it that the devices are speaking different radio languages? Or is the data formatted in ways that just don't match up? Or are the applications themselves unable to understand each other's requests? It helps you pinpoint the issue.
Okay, that layered view definitely clarifies the scope, and the material quickly points to something pretty fundamental for enabling all this communication, standards, and protocols.
Ah, yes, the bedrock. If interoperability is about understanding each other, then standards and protocols are basically the vocabulary and grammar that make that understanding possible.
Vocabulary and grammar, I like that.
Standards provide that common agreement on how things should work. They define, data formats, communication patterns, security mechanisms, interfaces, all that foundational stuff.
And without them,
Yeah,
chaos.
pretty much. Without standards, every manufacturer would just invent their own unique way of doing things. You'd end up with this totally fragmented mess where nothing works together natively, a digital Tower of Babel, if you like.
Okay, so standards set the overall rules. What about protocols then?
Protocols are the specific rules and procedures for actually transmitting and receiving the data. They dictate how data is packaged up, how it's addressed, how it's sent over a network.
So using your analogy, the standard is like agreeing on the format for a postal address, street, city, zip code.
Right.
And the protocol is like the rules for how the mail truck picks it up, sorts it, delivers the letter.
That's a great way to put it. They work hand in hand to make sure communication happens correctly and reliably.
Okay. But the material also emphasizes that standards are critical, yet the fragmentation still exists. So even with standards, we have problems. What are the main barriers stopping things from working seamlessly today?
Ah, yes, this really gets to the heart of the problem. And the fragmentation comes from several key obstacles. Even if the initial definition doesn't list them out right there, the whole discussion points to them.
Like what?
Well, a major one is the prevalence of proprietary ecosystems and vendor lock-in. Lots of companies design their devices and platforms to work best, or maybe only within their own closed system.
Right, keep the customer buying their stuff.
Exactly. It's a business strategy, plain and simple, but it fundamentally hinders interoperability with anyone else's products.
Makes sense. What else?
Another huge barrier is actually the proliferation of different standards and protocols combined with the lack of universal adoption.
So too many standards is almost as bad as no standards.
In a way, yes.
No.
As we'll get into, many standards exist, but not one has achieved truly universal acceptance across every industry or every type of device. So manufacturers pick the standard that suits their specific need or their market. Sometimes they even tweak existing ones slightly.
And that creates more silos.
Exactly. It creates a landscape where, say, a smart home device using standard X doesn't natively understand a device using standard Y, even if both standards are perfectly well defined.
It's like trying to have a conversation between someone speaking British English and someone speaking American English. Mostly okay, but sometimes.
Sometimes key things get lost in translation.
Yeah.
And then there's just this sheer complexity of integrating all these different systems.
You mean all the different bits and pieces?
Yeah. Think about a typical IoT deployment. You've got hardware from different vendors, software running on various platforms, edge, cloud, different network technologies, maybe connections back to old company systems.
Legacy stuff.
Right. Getting all those moving parts to talk reliably and securely, that's a significant technical challenge. It takes real expertise and effort.
So it's a mix of business strategy, just having too many technical options, and the inherent difficulty of connecting complicated things. But the sources also mention a key technology that acts as a bridge here, APIs.
Absolutely. Application programming interfaces, APIs, they are indispensable tools in navigating this fragmented world, especially at that application layer we talked about.
Okay, so how do they help?
Well, while protocols handle how data moves over the network, APIs define how different software applications or services interact at a higher level. Think of an API like a contract or a really well-defined front door that one piece of software offers to others.
A contract.
Yeah, it specifies what data it can provide, what actions it can perform, and crucially, what format the requests and responses need to be in.
Okay. And in IoT?
In IoT, APIs are essential. because they let developers access data from devices or control them without needing to know all the nitty-gritty details of the underlying communication protocol, which might be proprietary or just different.
Ah, so it hides the complexity.
Exactly. A cloud platform managing devices might offer a standard REST API, for example, that lets third-party apps grab sensor data or send commands using familiar web tech, even if the actual devices are using something totally different like MQTT or CoAP to talk back to the platform.
So the API is like a universal adapter plug.
That's a great analogy. They act as essential translators or universal adapters,
Oh.
presenting a simplified, standardized view of what the device or platform can do to the wider software world. It really cuts down the integration work for developers.
That's a powerful idea. API is sort of smoothing over the cracks between different systems. So
Uh,
for you, the listener, really getting your head around what IoT interoperability is,
uh,
recognizing those different layers, device, application, network, where problems can pop up,
right.
appreciating why standards and protocols are important, but also why they haven't solved everything.
Mm.
And then seeing how APIs act as these crucial bridges, it gives you a mental model,
Yeah,
right?
absolutely.
It helps you move beyond just saying, hey, these things don't talk to each other, to understanding why that might be happening and what kind of solutions, maybe adopting a standard, maybe using an API, maybe needing some kind of translation layer, are needed to actually fix it. It's like a framework for diagnosing the problem.
Yeah, it shifts the perspective. Instead of just it's broken, you can start thinking, okay, where is the communication breaking down? And that leads to more targeted solutions.
Which brings us very neatly to the current state of play, as explored in the next section of your material. Actually navigating this standard landscape. You mentioned it before, sometimes the problem isn't a lack of standards, it's having too many.
Indeed. Chapter 2 dives right into that diverse world of existing standards and protocols. And as the material implies, this very diversity is a huge part of the fragmentation problem.
How so?
Well, you've got loads of different standards, bodies, industry alliances, even individual companies, all developing protocols.
Hmm.
Often they're optimized for very specific things, certain use cases, certain network types, devices with limited power.
Right. Tailored solutions.
Exactly. But the challenge then becomes getting these different languages, these tailored solutions, to coexist or communicate effectively with each other.
And your sources specifically call out a few prominent ones, MQTT, CoAP, and Zigbee.
Yeah, those are 3 really good examples, each representing a different kind of approach or maybe operating at a different layer in the stack.
Okay, let's spend a moment on each. MQTT, that one comes up a lot. Often cited for lightweight messaging.
That's right. MQTT, which stands for Message Queuing Telemetry Transport, is incredibly popular, especially in scenarios where you have lots of devices, maybe with limited processing power, memory, or battery,
Constrained devices.
and often operating over networks that might not be super reliable.
Mhm.
Its big strength is this simple publish-subscribe messaging model.
Publish, subscribe. How does that work?
Basically, devices publish data on specific topics, think of them like channels, and then other applications or services that are interested subscribe to those topics to receive the data.
Ah, so the sender doesn't need to know who's listening, just sends it to the topic.
Precisely. It decouples the source from the destination. Makes it really efficient for situations where one piece of data needs to go to multiple places, like fanning out sensor readings.
Okay. And it's lightweight.
It's designed with minimal overhead, very efficient for those constrained devices and iffy connections. You see it a lot in remote monitoring, industrial IoT, even some consumer stuff.
Got it. Efficient for many devices sending data out, especially when resources are tight. What about CoAP then?
CoAP, the Constrained Application Protocol, is often talked about as the IoT version of HTTP, the protocol that runs the web.
Okay, so like HTTP, but for tiny devices?
Pretty much. It's a RESTful protocol, uses similar ideas like get, PUT, post, delete commands.
Mm.
But crucially, it's optimized specifically for constrained nodes and constrained networks. Think low power, maybe unreliable wireless sensor networks.
And how does it differ from MQTT's model?
Unlike MQTT's publish-subscribe, CoAP is mainly a request-response protocol, more like a client talking directly to a server.
So more direct interaction.
Yeah. It makes it well-suited for specific control actions, or maybe fetching data from one particular device. Think simple machine-to-machine interactions.
Okay, so if MQTT is like broadcasting messages on specific channels for anyone listening, CoAP is more like directly asking a specific device for something or telling it to do something using web-style commands, but very efficiently.
That's a pretty good way to simplify their core interaction models, yeah.
Okay. And then the third one mentioned is Zigbee. That feels different again.
It operates at a different level, yeah. Closer to the physical radio and the network layers themselves. Zigbee is really a specification for a whole suite of communication protocols used to create small, low-power digital radios.
Used where, mainly?
Particularly popular in home automation and some industrial settings. Its key feature, the thing it's really known for, is strong support for mesh networking.
Mesh networking, what's that?
In a Zigbee mesh network, devices don't just talk to a central hub. They can actually relay messages for each other.
Ah, like a bucket brigade.
Kind of. It creates a really robust self-healing network. If one path is blocked, the message can often find another way. It can cover a larger area and is pretty resilient if one device fails.
Okay. And what's it good for?
It's optimized for sending data periodically and for low latency when you need short bursts of data within a local area, like inside a building. That's why it's popular for things like smart lighting, sensors, control systems in homes or factories.
Right. So MQTT for efficient data transfer, maybe over unreliable or wide networks. CoAP for more direct web-like interactions with constrained devices. And Zigbee for robust local mesh networks, like in a smart home. It really shows how different tools are needed for different jobs.
Exactly. And the material points out that this very specialization leads straight into the next challenge.
Yeah.
Different industries and different applications naturally tend to favor the standards that best fit their specific requirements.
Makes sense.
So home automation might heavily use Wi-Fi and Zigbee. Industrial automation might lean toward MQTT and maybe specific industrial protocols. Smart cities could use LoRaWAN or cellular networks, maybe with MQTT on top for data aggregation.
And this sector preference just makes the fragmentation worse.
Significantly worse. Because a device designed and certified for, say, a home automation system using Zigbee might need a really complex gateway or some clever software layer just to integrate it into an industrial monitoring system built around MQTT.
Even if both are just sending temperature readings.
Even then, fundamentally, they're operating on different technological stacks, optimized for completely different environments and assumptions. They're speaking different technical dialects, rooted in the needs of their industry.
Right. And this leads us back to that difficulty of widespread adoption that the source talks about.
Yes, getting everyone or even just a large majority to adopt a single standard or even a harmonized set of standards is incredibly challenging. And it's a major bottleneck holding back truly seamless, widespread IoT interoperability.
Why is it so hard? What are the reasons the material hints at?
They're multifaceted. There's the competitive angle. Companies often see their own proprietary platform or their preferred standard as a way to differentiate, to capture market share. They might be reluctant to fully embrace open standards that help their competitors just as much.
The business strategy again.
Definitely. Then there are huge legacy investments. Companies have existing infrastructure, product lines built on older or proprietary tech. Moving away from that is expensive and takes a long time.
Can't just rip and replace everything.
Not easily, especially if it's critical infrastructure. Plus, there's often a perception, sometimes justified, that a specific standard is technically superior or just better suited for a particular niche, which keeps it entrenched there. This fragmentation isn't just technical. It's deeply tangled up with business strategy, market dynamics, history.
It makes total sense. Everyone wants their slice of the pie. And sometimes making your slice incompatible makes it more valuable to you, even if it means the overall pie for the industry doesn't get as big as it could.
Well put.
But the sources do mention some positive efforts, right? People trying to bridge this gap. It highlights organizations like the Open Connectivity Foundation, the OCF.
Indeed. Initiatives like the OCF are really crucial. They represent collaborative efforts trying to tackle this fragmentation head-on.
What's their goal, basically?
Well, as implied by their mission, it's to promote interoperability by developing and pushing open specifications. Specifications that allow devices and services from different manufacturers to find each other and communicate, regardless of the underlying hardware or operating system.
So they're trying to define a common language above the specific protocols.
That's a good way to think about it. They focus on defining a common application layer framework, common data models, security profiles, stuff that can work across various network protocols like Wi-Fi, Thread, etc.
Okay, so they're trying to build that universal phrasebook or maybe a middleware standard that lets devices describe what they can do in a consistent way.
Exactly. Even if the underlying tech is different, the hope is they can present their capabilities through this common OCF layer, making interoperability easier at the application level. It's an attempt to create common ground above the protocol diversity.
It's promising that there are groups trying to, herd these cats. So for you, the listener, when you're navigating the IoT world, You need to recognize that different devices use different standards, often tailored to their original purpose.
Hmm.
Understanding the basics of key standards like MQTT, CoAP, Zigbee, and appreciating the challenges of getting them to coexist helps you anticipate integration problems.
Yeah, sets expectations.
It explains why you often need things like gateways or translation layers. They exist specifically to bridge these divides, sometimes using frameworks like OCFs. Knowing this helps you figure out how complex it might be to integrate new devices into your systems.
Knowing the languages your devices speak is definitely the first step to finding the right translator.
That leads us very naturally into the role of edge computing, which is the next section in your material. This feels like a really practical approach, architecturally, that can directly help with some of these interoperability problems we've been discussing.
It absolutely does. Chapter 3 explores how edge computing, specifically in the IoT context, plays a really crucial role in managing all this complexity and the heterogeneity of devices and data.
So, what is edge computing in this context?
Basically, it means processing data closer to where it's actually generated, maybe on the IoT device itself, but more commonly on a local gateway or a server that's physically near the devices, at the edge of the network.
Instead of sending everything straight to the cloud immediately.
Exactly. Instead of shipping all the raw data off to some distant cloud data center for processing, you do some or all of it locally at the edge.
Okay, so distributing the processing power. How does doing that, bringing the compute closer, actually enhance interoperability?
Well, the main way, as the sources highlight, is that edge devices, especially edge gateways, can act as really powerful intermediaries and translators.
Ah, the translator role again.
Right. An edge gateway can be designed to understand and communicate with multiple different protocols and data formats used by the devices connected to it locally.
So it can talk to lots of different speakers.
Precisely. You could collect data from devices speaking, Zigbee, Modbus, MQTT, maybe even some old proprietary protocol.
Uh-huh.
It can perform the protocol translation right there, normalize the data into a common format like standard JSON, or maybe a structured industrial data model,
Okay, clean it up.
and then send this processed, harmonized data upstream to the cloud or to enterprise applications, maybe using just a single standard protocol like MQTT or HTTPS.
I see. So the applications further up the chain don't need to worry about all the different device languages.
Exactly. The upstream applications or the cloud platform, they don't need to understand the nitty-gritty of every single device's native protocol. They just need to integrate with the edge gateway. The edge effectively abstracts away a lot of that device-level interoperability headache.
That makes a ton of sense. The edge device is like the local conductor, getting all the different instruments in its section playing together nicely before sending a clean score up to the main conductor in the cloud.
That's a fantastic analogy. It really simplifies the integration architecture, especially for larger, more complex systems.
And the material notes some specific benefits beyond just easier integration, like lower latency and less bandwidth use.
Absolutely. Those are major drivers for adopting edge. Reduced latency is huge, especially for anything needing real-time control or immediate responses.
Because you don't have that round trip to the cloud and back.
Exactly. Sending data way up to the cloud and waiting for a response just introduces network delays. Processing data and making decisions right there at the edge dramatically cuts down on that round-trip time.
Give me an example where that's critical.
Think about industrial automation. A machine might need to react instantly if a sensor detects a problem. Sending that data to the cloud for analysis first is just way too slow. Edge processing allows for the kind of sub-millisecond response times you need for safety systems or really precise control.
Okay, speed is key. What about bandwidth?
Reduced bandwidth usage is the other big one. IoT devices can generate absolutely enormous amounts of raw data. Think high-frequency sensor readings, video streams.
Yeah, tons of data.
Sending all that raw data to the cloud is expensive, both in terms of data charges and network capacity. It can just overwhelm the networks.
So the edge filters it.
Right. Edge devices can filter, aggregate, analyze, and process this data locally. They only send the important stuff upstream, maybe just the key insights, alerts, or summarized data. This massively reduces the amount of data hitting the network, saves costs, lowers network load, makes communication much more efficient overall.
So it's faster and cheaper because you're not constantly shipping these mountains of raw data back and forth.
Makes sense. And the sources mention case studies showing successful edge implementations. We don't have the specific details, but what do those kinds of cases likely show in terms of solving interoperability problems? Yeah, even without the specific examples in front of us, you can be pretty sure those case studies would showcase how edge computing has been successfully used to integrate different systems that, previously couldn't talk to each other effectively.
Like connecting old machines to new systems.
Exactly. They likely highlight scenarios where edge gateways are used to connect legacy industrial equipment, maybe stuff using old serial protocols to modern cloud-based analytics platforms. Or maybe how they harmonize data coming from a mix of wireless sensors using different standards, like Zigbee and LoRaWAN, before feeding it all into a single management dashboard.
So proving it works in the real world.
Right. These cases demonstrate the practical power of using edge computing as a strategic layer to get over those technical hurdles, the different protocols, the inconsistent data formats in actual deployments. They provide concrete evidence that edge is a really viable architectural pattern for building more interoperable IoT solutions today.
It really underlines that edge isn't just about making things faster. It's a key strategy for achieving practical interoperability when you're faced with all this fragmentation. And the sources also touch on future trends for edge computing. Where's it heading?
Yeah, the material suggests the role of edge is only going to grow and get more sophisticated. We're likely to see edge devices and gateways become even more powerful,
How so?
capable of running complex analytics, machine learning models, maybe even sophisticated middleware, all locally on the edge device itself.
So more intelligence moves out of the cloud to the edge.
Exactly. This allows for more autonomous decision-making right there at the edge, reducing the reliance on having constant cloud connectivity. That further enhances localized interoperability and makes the system more resilient if the network goes down.
What might that look like in practice?
Future edge systems might feature things like dynamic protocol translation, figuring out how to talk to new devices on the fly, or intelligent data routing based on real-time network conditions, maybe even self-configuring capabilities to make adding new devices much easier. It really opens up possibilities for highly responsive, distributed IoT systems that can work effectively even in difficult or disconnected places.
Wow, so the edge could become incredibly smart, almost automatically handling more and more of the integration work. So for you listening, if your IoT projects are hitting walls with latency or bandwidth costs, or just integrating a real mix of devices,
Mhm.
understanding edge computing is pretty crucial. It gives you a powerful architectural option: process data closer to the source, improve performance, manage data flow better, and critically, use it as a practical bridge to achieve interoperability in these diverse environments.
It's definitely a key tool in the interoperability toolbox, especially as your deployments get bigger, and you inevitably have more different kinds of devices to deal with.
Okay, let's pivot now from the architecture, the where, to the who the individuals on the ground floor actually trying to make it all work. Section 4 of the source material really digs into the developer's perspective. What are the specific challenges they face when trying to integrate all these different devices and platforms?
Yeah, this chapter gets right into the practical, sometimes painful reality for the engineers and developers building these IoT solutions. It highlights that integrating diverse components is definitely not a simple plug-and-play task. It takes significant effort and throws up some distinct challenges.
And one major one identified is dealing with legacy systems.
Oh, absolutely. Huge challenge. Many organizations, maybe most, aren't starting their IoT journey with a completely blank slate. They have existing operational technology OT systems.
Like what? Factory controls? Building systems?
Exactly. Industrial control systems, building management systems, utility infrastructure, stuff that might be decades old. And these systems often use outdated communication protocols, things like Modbus, BTnet, maybe even ancient proprietary serial protocols.
Things not designed for the internet age.
Not at all.
Yeah.
They often have rigid data structures,
Yeah.
and they were designed long before anyone was thinking about IKE connectivity or cloud integration. So trying to connect modern IoT devices and platforms to pull data from or maybe send commands to these legacy systems, that's a massive technical hurdle.
Requires specialized gear.
Often, yeah.
Mm-hmm.
You frequently need specialized hardware gateways or specific software just to translate the communication signals and make sense of the data.
So it's not just about getting the shiny new smart widgets to talk to each other. It's getting them to talk to the old, maybe slightly rusty, but absolutely critical infrastructure that's already running the business. That sounds incredibly difficult.
It really is. And these legacy systems are often mission critical, right? You can't just tinker with them or easily replace them.
No downtime allowed.
Exactly. So integrating with them requires a deep understanding of their specific, sometimes poorly documented, protocols and data formats. It often means building custom connectors or using very specialized middleware designed for bridging that gap between the OT world and the IT world.
Speaking of middleware, the source discusses strategies for deploying middleware as a way to tackle these kinds of integration headaches. What exactly is middleware doing in this IoT context?
Okay, so in the IoT world, middleware essentially acts as a software layer that sits between things, between the devices, the applications, maybe the enterprise systems back at headquarters.
In the middle makes sense.
Right. And it provides services specifically designed to help with communication, data management, and integration. Middleware platforms are built to handle the complexity of connecting all these diverse components.
What kind of functions does it perform?
Oh, critical functions, like protocol translation, converting data from, say, MQTT coming from a sensor into HTTP that an enterprise application understands. Data transformation, mapping data points from different devices, which might call the same thing by different names, into a common standard data model.
Harmonizing the data.
Exactly. Data routing, figuring out where messages from specific devices need to go, which applications need to see them, and often managing things like device identity and security credentials, too.
So it's like the central switchboard and translation service.
That's a good way to think of it. It acts as the glue, providing this flexible layer that decouples the devices from the applications, instead of every single application needing to know how to talk to every single type of device.
Which would be a nightmare.
A total nightmare. They can just interact with the middleware. And the middleware handles the underlying complexity of the communication and the data formats. It really simplifies development and makes the whole system more maintainable and easier to scale later on.
It sounds like the unsung hero in many complex IoT setups.
Often it is. It's doing a lot of the heavy lifting behind the scenes to make these complex integrations actually possible.
And the source also notes that there are various tools and platforms out there specifically to help developers with this integration work. They're not totally alone.
Yeah, thankfully not. A whole ecosystem of tools and platforms has sprung up specifically to try and simplify IoT integration. While the source material doesn't name specific products, these tools often provide helpful features.
Like what?
Things like pre-built connectors for common devices, popular protocols, maybe standard enterprise applications like databases or CRM systems. Saves developers from building those connections from scratch.
Okay, ready-made adapters.
Right. Some offer visual development environments, drag-and-drop interfaces where developers can design data flows and integration logic graphically without writing tons of complex code.
Makes it faster, maybe more accessible.
Yeah, potentially. Features like data mapping tools, protocol adapters, device management capabilities, they're all common. The goal is always to reduce the manual effort and the specialized coding needed to get these different systems talking to each other.
So think of these as specialized toolkits, like an IDE, but specifically designed to make the painful job of IoT integration less painful.
That's a really good description. They're geared towards the unique challenges of stitching together all the disparate pieces of an IoT solution.
That's helpful to know that there are dedicated tools for this problem. So for you listening, if you're involved in actually deploying or managing IoT solutions, this section really underscores the significant technical hurdles involved in integration, especially with that legacy stuff. It shows that things like middleware and specialized tools aren't just optional extras. They are often essential strategies for successfully connecting everything in a way that can scale and be maintained over time. It helps set realistic expectations, maybe, about the complexity and effort involved.
Yeah, it really emphasizes that integration isn't just something you tack on at the end. It's a core engineering challenge that needs dedicated strategies and tools right from the start.
Okay, so moving from the problems developers face to the solutions. Section 5 of your source material shifts focus to actionable insights, best practices that developers can actually follow to proactively build for better interoperability from the get-go.
Right. This is about shifting the mindset. Instead of just reacting to integration problems after they appear, how can you design systems that are inherently more open, more flexible, easier to integrate from day one?
Designing for interoperability.
Exactly. And the material outlines some key practices for developers to really embed this into their design philosophy.
That was its first one.
One critical practice mentioned is using design patterns that promote interoperability. Now, the source doesn't list specific patterns by name, but it's talking about applying proven architectural approaches that make systems more modular, more flexible, and easier to connect with others.
What does that mean in practice?
It means designing components with really clear, well-defined interfaces, like using standard APIs or standard messaging formats. It means favoring loose coupling between different parts of the system.
Loose.
Yeah, where changes in one component have minimal or ideally no direct impact on other components. Makes the system less brittle. And it might mean adopting things like event-driven architectures, where components react to events rather than needing tight, direct, synchronous communication all the time.
So building with interchangeable parts, almost.
That's the idea. Building with these patterns makes it much easier down the line to swap out components or integrate new devices, new protocols, new services. If a new standard comes along, or you need to add a totally new type of sensor, a system built with this kind of flexibility can incorporate it more easily, maybe just by adding a new adapter or modifying one specific module instead of needing a massive rewrite.
It's like building with Legos that snap together easily, rather than, I don't know, welding everything into one solid, rigid block.
Exactly like that. Easier to modify and extend.
Okay, that makes sense. Another absolutely crucial practice highlighted is thorough testing, specifically across platforms and vendors.
Oh, this one cannot be stressed enough. Cannot. Just because your device or your application works perfectly fine in isolation, or maybe even within your own controlled test lab, using all the same manufacturer's equipment, that absolutely does not mean it will work correctly when it's deployed out in the messy real world, interacting with devices from different companies, running on different operating systems, or talking over unpredictable networks.
The real world is where the problems show up.
That's where interoperability issues often rear their ugly heads right at those seams between different systems.
Yeah.
So rigorous testing means creating test setups that actually mimic the diversity of the environment where this thing will live.
How do you do that?
It means actively testing the communication flows, the data formats, the security handshakes, the error handling between your component and a wide range of third-party devices, gateways, cloud platforms, network types, whatever it's expected to interact with.
You have to deliberately test the connections.
You have to actively test those seams where different systems meet. You need to validate that data is being understood correctly, that commands are interpreted as intended across all the expected integrations. You simply cannot assume it'll just work everywhere. You have to prove it. Test, test, test.
You have to deliberately poke and prod those points where different technologies connect. Okay. And the final best practice mentioned is building with flexibility and scalability in mind, right from the start.
Yeah, and this really ties back into those design patterns we mentioned earlier. Flexibility means the system can adapt over its life cycle, adapt to changes in standards, new technologies, shifting business requirements.
Future-proofing it.
Kind of, yeah. And scalability means it can handle growth, more devices, higher data volumes, more users, without the performance falling off a cliff or needing a fundamental redesign.
Why are both so key for interoperability?
Well, designing for both is essential for protecting your IoT investment in the long run. A rigid, non-scalable system might work okay today with a small number of devices, maybe all from one vendor.
Yeah.
But it will quickly become a bottleneck and probably a huge cost burden as soon as you need to integrate more diverse devices or expand your deployment significantly.
It hits a wall.
Exactly. Thinking about how the system will handle new data sources, how it might interact with platforms you haven't even thought of yet, how it will grow in capacity, considering that from the very beginning is critical for long-term interoperability and success. It helps prevent you from building something that's inherently incompatible with its own future needs.
It future-proofs your solution as much as possible against that constantly changing IoT landscape. So for you, the listener, whether you're a developer yourself or maybe you're involved in specifying system requirements, these are really concrete, actionable takeaways. Are the design choices being made prioritizing modularity and standard interfaces? Is that cross-vendor, cross-platform testing a non-negotiable part of the whole development process? Are the architectural decisions truly considering flexibility and scalability for future devices and integrations?
Yeah, asking those questions is key.
Prioritizing these practices up front, as the source suggests, seems like it could save significant headaches, delays, and costs down the road.
Absolutely. Building interoperability in from the start is a strategic decision. It's an investment that pays dividends over the entire lifespan of the system.
Okay, shifting perspective one more time. Section 6 in your source material takes a look at this whole issue from the business side, the crucial management perspectives for, say, tech leaders and decision makers. Because interoperability isn't just a technical detail buried in the code, right? It has profound implications for business strategy and investment.
Absolutely. Chapter 6 really zooms out and addresses how these technical challenges, specifically interoperability, directly impact strategic business decisions.
Hmm.
For leaders, it's really imperative to understand this connection.
What's the core message for them?
That business goals relying on IoT capabilities, whether that's optimizing supply chains, offering fancy predictive maintenance services, creating smart building solutions, developing new consumer experiences, whatever it is, those goals must be realistic. They have to be aligned with the underlying technical ability of the devices and systems to actually communicate effectively.
So the tech has to be able to support the business dream.
Pretty much. You might have a brilliant business concept that requires combining data from, say, manufacturing equipment, logistics sensors tracking shipments, and maybe external weather forecasts.
Sounds valuable.
Potentially very valuable. But if the platforms managing those different data sources simply cannot interoperate, maybe due to technical barriers or vendor lock-in issues, then that brilliant concept either cannot be realized or it's going to require enormous, costly, time-consuming custom integration efforts just to make it happen. The desired business outcome has to be grounded in the reality of what's technically feasible in terms of connecting things and exchanging information.
So business strategy needs to be informed by the, let's say, connectability of the technology. And of course, this has major financial implications.
Oh, enormous financial implications. The source clearly points this out. Lack of interoperability is expensive, sometimes cripplingly expensive.
How so?
Well, it leads directly to increased development costs because your teams are spending time building custom integrations for every single connection point instead of using standard methods.
Reinventing the wheel every time.
Pretty much. It creates massive integration headaches leading to project delays, deployment failures, and then ongoing maintenance burdens because all those custom connections are fragile and need constant attention. It results in vendor lock-in. If your systems only work with one vendor's products, you're stuck. That restricts your choices, weakens your negotiating power, and can really stifle innovation because it's hard to bring in maybe a best-of-breed component from a different supplier.
And missed opportunities.
Definitely. You just can't deliver the full potential value of IoT or unlock new revenue streams if your data is trapped in silos and your systems can't cooperate effectively. The opportunity cost can be huge.
Okay, so lack of interoperability costs money, time, and opportunity. What about the flip side?
Conversely, prioritizing and achieving better interoperability is actually a really sound business investment. It directly reduces development and integration costs. It speeds up time to market for new solutions and services.
Makes you more agile.
Exactly. It enables greater agility and flexibility. It helps you avoid vendor lock-in. And it allows organizations to leverage data and capabilities across different systems to create genuinely new value propositions. It directly impacts your competitiveness and, ultimately, your profitability.
So interoperability isn't just some line item for the IT department's budget. It's a really fundamental strategic factor influencing the viability and profitability of the whole IoT initiative.
That's the key message for leadership.
And because it's so critical, the source argues it needs to be explicitly part of how you measure success.
Yes. You need to measure it to manage it, right?
Mhm.
Success metrics for an IoT deployment shouldn't just be about, say, the number of devices you've connected or the sheer volume of data you're collecting.
Need more than vanity metrics.
Right. They should include metrics directly related to interoperability. Things like, how effectively does this system integrate with other key platforms? How easily can we add new devices, regardless of who made them? How reliable is the data flow across these different components? Maybe even track cost savings achieved through more streamlined integration processes.
Okay, so measure the connectability itself.
Yeah. These kinds of metrics help tech leaders actually demonstrate the tangible value of investing in interoperability, and they help align the technical efforts with the strategic business outcomes everyone's aiming for.
It forces a focus on whether the whole ecosystem of devices and systems is actually working together as a cohesive unit to deliver real business value. So, for you, listening, if you're in a leadership role or involved in making decisions about IoT investments, this section is a clear message. Interoperability isn't some minor technical detail you can just delegate and forget about. It's a fundamental strategic consideration. It impacts your budget, your timelines, your vendor relationships, your risk profile, and ultimately, the success or failure of your IoT ambitions.
You really need to understand it, prioritize it, and include it in how you define and measure success.
It's either a strategic enabler helping you move faster, or it's a critical inhibitor holding you back, depending on how you address it.
Well said.
Okay, finally, as the source material wraps up, it looks ahead. It peers into the future of IoT interoperability. Because this is obviously a really dynamic space, right? What's a challenge today might be tackled very differently tomorrow.
Indeed. The final section tries to forecast how this landscape is likely to evolve. And one key prediction is a continued evolution of existing standards alongside the emergence of new technologies.
So no magic bullet standard is going to appear and solve everything.
Probably not. It's unlikely we'll see one single standard conquer all. Instead, existing ones will likely be refined, maybe adapted for new use cases, perhaps integrated better through collaborative efforts like the OCF we discussed, and new protocols and frameworks will undoubtedly appear.
Why new ones?
To address emerging challenges, like managing IoT at massive scale, or dealing with new types of networks, or meeting enhanced security requirements that we haven't even fully grasped yet.
So the churn continues.
Pretty much. Which means it's staying informed and especially maintaining that architectural flexibility we talked about in the best practices section is going to be an ongoing necessity. You have to be ready to adapt.
The future implies maybe an accelerating pace of change in the standards world, requiring constant adaptation. And one of the potentially really disruptive forces mentioned is the impact of advances in AI and machine learning. This is where it gets kind of mind-bending, potentially. How could AI and ML fundamentally change the interoperability game?
Yeah, this is where things get really interesting. Think about what AI and ML are good at: pattern recognition, anomaly detection, sophisticated data analysis, even natural language translation.
Okay.
Now, apply those capabilities to the interoperability problem. AI could potentially become an incredibly powerful, dynamic layer helping things connect.
Like, what could it do?
Well, imagine AI algorithms analyzing network traffic, looking at the data streams coming from various devices, and automatically identifying the different protocols being used, figuring out the data formats, and then learning how to translate between them on the fly.
Without needing explicit rules for every single translation.
Potentially, yes.
Mm.
Without requiring developers to hard code rules for every single possible interaction.
Mm.
The AI could build its own translation models based on observation.
What else?
AI might be able to predict where integration issues are likely to pop up, maybe based on subtle patterns it sees in the data or device behavior. It could then dynamically optimize communication routes or choose the best translation method in real time to avoid problems.
So it could become like an intelligent traffic cop for data.
Or maybe like a super intelligent self-configuring middleware or edge layer, dynamically solving interoperability problems that currently take hours and hours of manual coding and configuration. It could be the ultimate translator, right? Capable of making almost anything talk to almost anything else just by watching how they try to communicate.
Wow, that's a powerful vision. An AI that just figures it out rather than needing detailed instructions for every single device type and protocol version out there.
It could dramatically reduce the burden of manual integration. It can make the whole IoT ecosystem much more fluid and much more adaptable to new or unforeseen devices or data sources.
Are there downsides, challenges?
Oh, absolutely. Implementing this kind of AI-driven interoperability brings its own huge set of challenges. You need massive amounts of data to train these models, significant computational resources. You need to ensure it's reliable and secure, manage the complexity of these autonomous systems. It's not easy.
But the potential is huge.
The potential is definitely there to address fragmentation at a much higher level of abstraction, moving away from rigid, predefined rules towards dynamic, intelligent adaptation.
So based on this forward look, the source seems to imply that preparing for this future means, again, embracing flexibility in how we design systems,
Crucial.
staying aware of how standards are evolving, and maybe actively starting to explore how technologies like AI and ML could be integrated into future strategies for managing these complex, heterogeneous IoT environments.
Exactly. It positions interoperability not as some static mountain you climb once, but as an ongoing, evolving challenge. And new technologies, like AI, will constantly offer new tools and approaches for bridging the gaps. Staying informed about these trends, like the potential for AI-driven translation, is really key to navigating that future effectively.
The future of interoperability might be less about finding the one perfect standard and more about building systems with intelligence and adaptability built in.
That seems to be the direction things are heading, yes.
Okay, wow. This has been a truly comprehensive deep dive into what is undeniably a complex but absolutely essential topic. We started by really defining IoT interoperability, breaking it down into those critical layers: device, application, network,
The foundations.
and understanding the fundamental role of standards, protocols, and especially APIs in trying to create some common ground in what's clearly a fragmented world.
Right, the tools we have now.
Then we navigated the current standards landscape, looking at key examples like MQTT, CoAPI, and Zigbee, and acknowledging those big challenges like different industries picking different standards, and just the difficulty of getting everyone to agree.
The reality of the fragmentation.
We then explored how edge computing offers a really powerful architectural strategy to help deal with that fragmentation, bringing processing and translation closer to the devices, giving benefits like lower latency and reduced bandwidth use.
A practical solution pattern.
Then we got into the trenches, looking at it from the developer's perspective, confronting those difficulties, like integrating with legacy systems, and highlighting how essential things like middleware, tools, and platforms are for managing all that complexity.
Yeah, challenges on the ground.
From there, we pulled out those actionable best practices for developers. Designing with flexible patterns, really committing to thorough cross-platform testing, and building for scalability right from the very beginning.
How to build better.
We also brought in that crucial business perspective, understanding how interoperability isn't just a tech cost, but a major strategic factor impacting business goals, financial outcomes, vendor relationships, and ultimately how you even measure success for an IoT project.
Why it matters to the bottom line.
And finally, we looked ahead, considering that continuous evolution of standards and the potentially transformative, maybe even disruptive role that AI and machine learning might play in dynamically solving these interoperability challenges in the future.
Yeah, the material you provided really hammers home that interoperability is not just some technical footnote somewhere. It's absolutely critical. It impacts every single facet of the IoT ecosystem, from the engineer working on the device firmware all the way up to the CEO setting the business strategy.
And as the source summary emphasizes, for developers, maybe the key takeaway is be proactive. Focus on that design flexibility. Religiously adopt those best practices for testing and scalability. Don't just hope things will be compatible. Build for it.
Absolutely. Assume nothing, test everything.
And for management, for the decision makers, it's really about ensuring that business strategies are grounded in reality, aligned with the actual technical integration capabilities, recognize the real costs of fragmentation, and maybe strategically invest in architectures like edge or middleware and processes that prioritize making things work together.
Treat interoperability as a strategic investment, not just a technical problem.
Ultimately, as the source concludes, achieving better interoperability, that's how we move beyond just having a collection of isolated, single-purpose smart devices to actually unlocking the full potential of the Internet of Things. It enhances the user experience, makes the technology feel seamless, intuitive. It drives innovation by enabling new combinations of data and functionality across systems that couldn't talk before. And it boosts competitiveness by letting organizations be more agile, more efficient, more capable of delivering new value. It really is, in so many ways, the key that unlocks the future of IoT.
It's the difference between having just a bunch of interesting but separate gadgets and having a truly intelligent, interconnected world that works together.
Yeah. And that leaves us with a final thought for you, the listener, to maybe mull over as you reflect on this deep dive. Given that fragmentation is the reality today, and achieving that seamless communication is so fundamental to unlocking potential and driving innovation, consider the devices and systems you interact with daily. Or maybe the future solutions you envision in your own field. What groundbreaking application, what critical insight, what amazing leap forward in efficiency or convenience is currently being held back, perhaps totally invisibly, simply because the necessary devices or applications or data sources just can't truly talk to each other yet. What innovative future is just waiting out there, right beyond this barrier of interoperability, something to explore on your own?
That's a powerful question. What potential are we missing out on right now?
Indeed. Well, this has been an incredibly insightful deep dive, and honestly, it was made possible entirely by the really valuable source material you shared with us. So we really appreciate you bringing this important topic to our attention.
Yeah, thank you for the opportunity to explore this. It's a critical area.
Until next time.